The next presentation is Jurga, identification and characterization of yellow archaeological glass beads found in Lithuania. Welcome.
Good afternoon, everyone. I am glad to attend the Baltic States Restorers meeting and present a 10 years long study which is designed to change our knowledge of the chemical composition, technological features and possibilities of the production of glass beads found in Lithuanian cemeteries. We don't have reliable knowledge of glass making in Lithuania until 16th century. We know about the use of glass in the first centuries from archaeological finds. Most of them is glass finds, is glass beads, usually found in the graves of the women and girls. Single ones as amulets are also found in men's graves. These glass beads are similar to early medieval necklaces found in Western and Central Europe, Scandinavia, and Middle East countries during archaeological research, both in terms of color, shape, variety of shape, proportions, as well as methods of decoration. Till now, glass beads found in Lithuania were mostly described and classified by archaeologists only visually according to their color and shape. However, their chemical composition haven't been carefully analyzed. Necklaces are considered to be one of the first man-made jewelry. They have always been a valuable piece of jewelry, often a sign of wealth. We can see nickel from Kernavė Kriveikiškės cemetery, which in 2007 went to Pranas Gudynas Restoration Center and started this long wait of research. We have very little research done, so this kind of research can be considered as pioneering work. The nickel looked very decayed. Visually, they looked more like ceramic than glass beads. They could be described as opaque, irregularly shaped from 1.5 to 3 millimeter in diameter and split. The surface of the beads of the second nickel was mated, but in view of the cross-section, we can see three zones: whitish bead surface, the opaque bright yellow zone, and the glassy yellow core of the bead. The beads of the third nickel look very similar, very similar to the second one. The main aim was to determine the chemical composition of the beads and characterize their materials. We focus on the study of the coloring components and the morphology of the pigment. Also described the process of the glass destruction. A combination of optical microscopy, some elemental analysis, X-ray diffraction analysis, micro-Raman, and ER spectroscopies were applied. The SEM elemental analysis was carried out to compare composition of beads in different areas. In corroded bead SEM image, B pictures, we can see lead tin oxide as white particles distributed in weathering lead-rich glass. Note that leaching of lead oxide from the glass due to weathering, which results in a lower average atomic number of the glass and hence a darker shade of the gray in the image. We can describe yellow bead core, same image C pictures, as lead-rich glass, gray color, in which are lead tin oxide from 2 to 5 micrometer spherical form, evenly distributed grains. This observation we confirmed by elemental analysis in individual glass beads zones. Elemental analysis shows that the contents of all yellow beads are high in lead, tin, and silicon. Calcium, aluminium, phosphorus in the range of the 2% by white were detected only in the surface areas. According to the obtained date, it can be presumed that the yellow beads were made on the rich lead silica glass matrix, which was colored with the lead tin yellow pigment. The dominant compounds in the composition in the surface layers were carbonates and maybe phosphates. They could be considered as products of glass destruction in the soil. The elemental composition results in the beads are similar to those described before. Indifference is that amount of silicon was determined 3 times less, calculated atomic ratio of the lead and tin in the bead, and level of silica is characteristic of lead tin yellow type 2 pigment. Also, the thumb image of the yellow bead sample shows the presence of 2-3 micrometer spherical form of crystallites that are distributed evenly with a tendency to form solid structures. It leads us to the conclusion that lead tin yellow type 2 pigment prevails in the composition of the bead. The question arose whether it is possible that the glass beads were made on the basis of the lead tin yellow type 2 pigment. Diffractograms showed that all significant reflections of the beads samples were assigned to the lead tin silicon oxide phase having a cubic structure with structures described the lead tin yellow type 2 pigment. All the bands visible in the yellow bead Raman spectrum coincide well with the comparative data of the lead tin yellow type 2 pigment. I would like briefly to discuss the chronology of the production and use of one of the most historically interesting pigments. It's the lead tin yellow pigment. The pigment has 2 chemically distinct forms, type 1 and type 2, which are determined by ratio of material used. Lead tin yellow compounds were applied extensively as coloring for glasses, enamels, and glazes in Roman and post-Roman period, and were frequently used in European paintings from 14th to 18th century. By scientists, it could be summarized that only lead tin yellow type 2 pigment is found in archaeological glass finds, while both forms of pigments are found in easel and wall paintings as well as in polychromy artworks. Supposedly, at first, pigment lead tin yellow type 2 was made as secondary glass-making products, and after discovery of usage was produced on purpose. When mixtures of lead tin yellow, when mixtures of lead and tin oxides are heated, it results in lead tin yellow type 1 pigment that has orthorhombic forms. Lead tin yellow type 2 pigment is obtained by heating a mixture of lead tin oxides as well as quartz and has crystalline cubic form. Lead tin yellow type 2 pigment, according to chemical composition, can be considered as lead glass, but unlike glass, which is amorphous, the pigment has a crystalline structure. This allows for successful identification by XRD and Raman spectroscopy, even if it is in a glass as matrix. After research, some uncertainty remained. What is a whitish surface of the bead like a crust? In slide, you can see presented here spectroscopy results of composition analysis of beads in different areas. Yellow marked bands, which were identified in the opaque bright yellow zone, coincide well with the comparative date of lead carbonate. We state that lead carbonate formed in the lead silicate glass through a corrosion process, while opaque bead on the whitish surface are linked to calcium phosphate, which developed due to long interaction between the glass materials and the archaeological environment. We concluded that two yellow beads were linked to lead silicate glass colored with lead tin yellow type 2 pigment, but third of yellow glass bead was produced directly from lead tin yellow type 2 pigment without being mixed with any colorless glass matrix. Despite the clearly formulated conclusions, a doubt remained because only a few conducted studies and our conclusion could be compared with published scientific works. We were not able to find literature demonstrating that yellow glass beads were made of the lead tin yellow type 2 pigments. However, scientists in analyzing of the yellow Islamic and Venetian enamels composition have stated that for production of this coloring, the lead tin yellow type 2 pigment was used directly without being mixed with any colorless glass matrix. Analysis of pigment production process have indicated that exists optimal ratio of components and optimal annealing temperature leading to homogeneous polycrystalline lead tin silicon oxide phase. This answered question prompted to check the collection of data of yellow glass beads stored in the National Museum of Lithuania in order to increase the scope of the research. We have selected 12 yellow glass beads found in various Lithuanian cemeteries. All of them were found singly in graves, but not in necklaces. These are glassy yellow beads, different form, ribbed, double beads, cylindrical, which size was about 1 centimeter. All of them look like glassy, retaining its shape and structure. The main question that arose was, why does the condition of glassy beads vary so much if compared with described before? From the presented images, we can see point destruction damages of the surface of the beads, layer of glass formation, and uneven distribution of yellow particles. The same combination of instrumental analysis was applied as for yellow opaque beads. Some images show that the bead matrix is composed of a homogeneous solid mass in which spherical pores are visible. In this glass matrix, gray contains non-uniformly distributed particles of various size, visible as white, bright dots. Elemental analysis of these dots revealed a high level of tin and lead. This suggests that it could be lead tin yellow pigment particles. The elemental analysis showed that contents of glass yellow beads matrix are high in silica, sodium, calcium, magnesium, and potassium. The results indicate glass matrix is mixed alkali-lime silica glass. Unfortunately, to determine the lead tin yellow pigment by XRD method was unsuccessful because the matrix of the beads are amorphous materials and the relatively small concentration of the pigments, although its grains are very clearly distinguished. However, a summary of Raman scattering spectra of yellow beads shows all the bands attributable to lead tin yellow type 2 pigment. The general conclusion is that visual differences between glassy and opaque yellow beads colored by lead tin yellow type 2 pigment are due to the different degree of the glass matrix destruction. In a dry environment, any type of glass does not change for a long time. The chemical destruction depends on the chemical composition of glass matrix, and it is in interactions with external factors, the most important of which are water or humid environment. Lead glass is quite soft, therefore it is relatively easily mechanically damaged, and such glass is easily affected destruction, especially when the environment is acidic. The analysis of chemical composition and structures of beads provide important information on the technological features of the production of glass beads, but in my opinion, too little research has been done for the chronological description of beads production. I would like to send my best regards to my best colleagues in Dratuna that followed me in this long research journey. And you can see a few photos from our scientist visit in Ljubljana. Thank you for your attention.